चलो जब तक एक क्वेश्चन पूछता है ऐसी. Suppose there is a rectangle, okay, a rectangular cake, let's say. Now in that you have cut another rectangular piece of cake. You have cut out another rectangular piece of cake. Now, and that rectangle can be oriented in any, you know, in any direction, or can be of any size. Now you want to divide that rectangular cake into two parts. How would you do that? Uh, so was yeah, a rectangle, and now there's a piece has been cut out of it from it can be from anywhere, like in between any place, and it's oriented like from the top you have to cut, like you can so that you cannot cut it from like let's say from the middle. You have to cut from the top, and so if it was just a rectangle, you could have cut it very easily, right? Now there is a cutout already, another rectangular cutout from the cake, and which is oriented in any like can be in any direction and of can be of any size. Now you have to cut this cake into two parts. Cut the leftover cake into two parts, two equal parts. Okay. Uh, from the husk. Okay, let's say you can you can see this piece, right? Uh, let's say now this rectangle is like this was a piece of cake, and I've cut this piece already. Now you have to now this piece is gone. Okay, this piece is gone. Now you have to cut the leftover into two equal halves. How would you do that? Okay, anyone? Okay, fine. Uh, Okay, thank you. Okay, so let's start. So today's topic of my talk is photo-reflectance spectroscopy study of bulk MoS2. Okay, before going into the actual study, I just wanted to talk about these the spectroscopy part, like the experimental part of it first. So let me first talk about the photoreflectance. Now, in order to understand photoreflectance, let's first go even to the even easier part, the reflectance. So, if you want to study the optical response of a material, one of the easiest thing that you can do is to measure its reflectance spectrum. And how do you do that? So, you can have this kind of a setup. Here, there's a lamp, which is a white light source. That is, it has a broad spectrum. Uh, it can give out many wavelengths of light, and then you pass it through a monochromator. So this monochromator is basically it has a diffraction grating which disperses this white light into various wavelengths, and then it has a input slit and an output slit. So you can select a certain wavelengths to come out of the exit slit, and then you can rotate the grating, and you can select whatever wavelength you want out of this monochromator. And then this we can call it as our probe beam. So this probe beam hits your sample, which you can place in a cryostat to cool it to whatever, like we can go down till 4.2 Kelvin, and then the reflected light comes on to our detector, which can be silicon photodiode or PMTs. So this detector will give you a response, which is usually a current corresponding to the intensity of light which is falling on it. This current you convert to voltage using a I2V converter, because voltages are easier to measure, and then you measure it through a lock-in amplifier. So I guess everyone here knows what a lock-in amplifier is. Uh, so uh, okay, just in any case, lock-in amplifier is basically a very good filter. It improves the signal to noise ratio of our sample, of our measurement. And how it does it is, this light, if you just pass on a DC light, like this lamp will give you a DC response, right? It will be constant over time, and this light also will be DC. But now, instead of having a DC light, let's say I put a chopper in front of this. The chopper is just like a fan. So what it will do is, it will sometime it will allow the light to pass, sometime it won't allow the light to pass. So you've converted this constant stream of light into a square wave. And now you know what is the frequency at which the chopper is operating. You feed that frequency to the lock-in amplifier, and now your response is also at that frequency only, and you feed your response to the lock-in amplifier. Now the lock-in amplifier, what it does is, it only measures the part of the response which is riding on this frequency, and it will suppress all the other responses. So even if the detector was seeing other light which was DC or some higher frequency thing, or electronics also pick up responses at the supply line frequency, let's say 50 hertz or higher harmonics, all those get suppressed, and you get a very good signal to noise ratio. So that is the advantage of using a lock-in amplifier, and this is known as a phase sensitive measurement. And now, okay, so using this kind of setup, you can plot reflectance versus energy. Here energy refers to the photon energy of the light that you are shining on the sample, and you can get these kind of responses. So this was reflectance. Now in photoreflectance, we have, yeah, what? Yeah, I can hear you. So we usually use something around 200 hertz. The highest that we can go is to 1 kilohertz. And actually, it depends on what kind of chopper you're using. If you use more blade, chopper with, uh, let's imagine chopper as a fan. So in a fan in your home, you will have like three blades. Now you can increase the number of blades to get the frequency will increase, but like there will be a physical limit to how fast you can operate. So usually you can go to kilohertz, a few kilohertz, but we did not go to. Hmm? Huh. Okay. So the thing is, this uh, the lamp light that is coming, it will have a spot size. Okay, the lamp light, you're focusing it onto the slit, it will have some size. Now if that size is very small compared to your chopper width, the blade width, then it is an ideal square wave. When you are cutting it, you will have an ideal square wave. But if it is, of the order of that blade width, then your the square wave will turn into trapezoidal, or if it's even bigger, then it will turn into a triangular wave. So the best response you will get when it's a good square wave. So that's why you try to keep the, uh, you don't want to introduce too many blades into the chopper. So otherwise the blade size will reduce and this thing will turn into a trapezoidal wave. So there's a play of like how. So usually we find that somewhere around 200 hertz is good enough for our measure. Okay, because you have this 1/f response of noise. So as you go higher in frequencies, your this background noise keeps decreasing, and right about, let's say, 180, 175 hertz, we see that we are in good territory. Okay. Okay. Next. Now let's move on to what is photoreflectance. In this, we have the same lamp monochromator. This is a probe beam falling onto the detector. Additionally, we have put a laser here. Now, what do we mean by laser? Laser is basically a source which is much more intense than the probe beam, or let's say 100 times or 1,000 times. And then we have placed a filter in front of the detector. So this laser is falling onto the sample, but this filter is avoiding any reflected light of the laser coming onto the detector. So we are not measuring the laser. We are not detecting the laser, reflected laser. What it is doing is actually perturbing our sample because it's an intense source. It is actually disturbing our sample, and this probe beam is now measuring that disturbance. How? So now we have moved the chopper from in front of the lamp to the laser. Now this probe beam is a DC light now. So our detector will measure it, convert it into I to V, and then will in the DC voltmeter will measure the probe beam in the DC mode. But this laser is perturbing our sample. Sometimes it's on, sometimes it's off, and so now this perturbation is riding on some frequency which is being fed to the lock-in amplifier, and now our signal is whatever is changing because of the laser, whatever is the change in the reflected spectrum because of the laser is what will pick up in the lock-in amplifier. So we have both the DC part, and now the AC part is the change in reflectance. Okay, let me explain it further. So we use this to measure semiconductors, and semiconductors have a conduction band and a valence band. And in the pump off situation, when the laser is off, at the surface of the semiconductor, there is a asymmetry because there's a change in the dielectric environment. So usually you find a slight bend. This is exaggerated here. There's a slight bend in the bands. This can also be due to at the surface you might have some dangling bonds because your structure is not complete there. The bonds are not all satisfied, so there are some dangling bonds. So charges get trapped at the surface. So you have this because of this charge trap. There's slight bending. Now, so the laser that you're shining, the photon energy of that laser has to be higher than the band gap of this material. And when you shine that, you will generate electron and hole pairs. Okay. Now these electrons and holes will recombine with the charge traps here at the surface. So their numbers will reduce, and so the bandages, this bending will reduce. Because this bending is reducing, so the electric field here will be changed. So here now the dielectric constant near the surface, because of this field, will also get changed. So these are the two conditions: pump off and pump on, and because of that, there is a change in the dielectric constant, which I've mentioned it as delta ER. Now this delta ER.
So I have two questions. First, this band is in real space, isn't it?
Yeah, this is in real space. Yeah, energy sample depth.
Yeah, so in real space, we actually expect that these bands will basically, it should be straight.
So that's what I'm saying. So that's why I'm saying. So that's why I'm saying that this is exaggerated. The bend won't be this high. There will be slight bend towards
some bending. there will be some bending. So my question is why it will bend actually at the edge of this at the surface actually.
At the surface, because there's a you know, that's what I told. There can be dangling bonds. No, let's say you have
So
silicon.
which way it will bend actually? So it will go towards higher energy sides or it will go towards the lower energy side?
Well, that depends
Well,
on.
here I see that these are actually going towards the higher energy side, I guess.
Mhm, mhm.
So
So
it
that
will,
it depends on what is the kind of charge carrier concentration at the surface.
okay.
So what kind of charge carriers are being trapped at the surface based on that. So this is like uh, so we, let's say we don't know what which way it's bending. We just know that it's being changed by the laser light.
Yeah, of course we expect that at the surface the atomic
There'll be
distributions are not as similar to the bulk sample, so there will be a
yeah,
difference.
yeah.
It's
And
just I
now
wanted to know whether it will go upwards or downwards.
so that is
That will
uh,
basically it will depend on the type of charge that we have on the
charge
surface.
that is being trapped there. Yes. Hmm?
But surface is expected to be neutral, I guess.
Uh, why is that?
No, if it is not neutral, then I mean, there should not be any charge on the surface. If there is a charge on the surface, then it will basically trap the oxygen atom or something from outside the surface, and it will basically get neutralized. I mean, all the surfaces that we have, normally,
Mhm.
whichever surface, like if you cut a wire, you will get a surface. That surface is not a charged surface. That's a neutral charge, neutral surface. Means any
So,
type of surface that
that's
we
why
have.
I've shown like uh, okay, it's not charged, but there is a field present.
There is a potential gradient I can
Yeah.
understand.
So,
There is an
so
electric field because the potential inside the sample and the out at the surface is
you
different.
cannot say that the surface is charged. Nah? So the whole
The
sample
surface is
is
not
neutral
charged.
because you haven't created any.
Yeah. So as
You
I
have just
understood that,
introduce a distribution, like
yeah. So
charge carrier distribution
I think
has
you are
changed.
saying, I think you are saying that a surface is electrically neutral, but
Huh.
there is a
There is
potential
because
gradient
there's
because of that some
because the distribution has
electric field.
changed. So
Okay.
there's an electric field. So I'm not saying it is charged.
Okay.
Yeah. Okay. So there's a delta ER, which will lead to delta N and K, which are the refractive indices, real and imaginary part, and which will generate a delta R. So delta R is the change in reflectance. And now this delta R has derivative nature. What I mean by that is uh, whatever was your R, when you are measuring delta R, it will be if there's any weak feature, its derivative will come up. Okay, let me explain, show it better with a measurement. So these are reflectance and photoreflectance measurement on bulk gallium arsenide. So and this is at 10 Kelvin temperature. So in R, you see there's a small feature here, and the reflectance is fairly constant. There's a small, it's going down with energy. This is photon energy. Okay, there's a small dip here in R, and when you measure photoreflectance, you see a huge signal corresponding to that peak. And there are some things to notice here. First, this here I've plotted delta R by R. It is this delta R by R is riding on a zero background. So wherever this, so because of dielectric constant, you are getting this R, and wherever this is constant, that means there is no feature here. You are getting a background dielectric. The change delta, you don't expect anything in the derivative also, because the derivative also is constant, so you get a zero background. And now whenever
Vishwas, I have once more. So the left hand figure that you plot the reflectance. So what is that actually? So you measure the reflected light and you convert it to a voltage, and from there, how are you getting this reflectance?
okay. So what we do is, let me go back and so first you put your own sample, whatever you're
Yeah.
measuring, you get a response. So that response is signal, whatever is signal, as a function of photon energy. Okay.
Yes.
Next, you put a known sample. So in our case, we put aluminium.
Okay.
Okay. Now like it's in literature, what is the aluminium response in the wavelength that you are measuring, and
Okay.
usually it's very it's flat, like it doesn't change much. Okay, so the metals in the optical range, their response is very flat. So you measure the aluminium response also,
Okay.
and that okay, it's 90%, 91%, that kind of reflectance it has. Now you divide these two signals.
Divide. I see. You just normalize the thing with aluminium's data.
And okay, it response was supposed to be 90%. So in this way, you have actually neglected all other responses, because in the
I see.
two data you have used the same monochromator, the same lamp, the same lenses,
Yeah. Yeah.
the same detector. So you have you have negated all their responses. So you only get the sample response. The sample is the one thing that you have changed in the two measurements.
So when you measure, so you also simultaneously place aluminum
Aluminum.
along with your sample. Okay.
So we measure both of them.
Okay. Thank you.
Okay. And so that's why I can say this is 35% reflectance or such things.
Vishwas, why there is a dip or peak?
Here.
Huh?
So I'll come to that, what this is.
Okay.
But first I'm saying just showing the difference. In the reflected spectrum.
You used a laser pulse also, no? What is the intensity of that laser pulse? Means in terms of electric field or something?
Okay, so in terms of microwatt, I know it's somewhere around 400 microwatt, and my spot size is what is 3-4 microns in diameter. So you can actually calculate what is the.
Yeah, it should be 1/2 epsilon 0 e square, I guess.
1/2 epsilon. Yeah.
Something intensity is directly proportional to some e square.
You need to know that this is a very it's much more intense than the probe light. Okay. So you get this kind of feature corresponding to this, and then here you don't see, you cannot make out is there any feature here, but in PR you can actually see something. So that is the advantage of using photoreflectance, that you might see some new features which are absent in the reflected spectrum. So it gives you more information about the sample. That is why we use photoreflectance. And but one thing to notice is this delta R by R. This is 10 raised to the power -4. So it is 4 orders of magnitude smaller than the R signal. So you actually need a very good signal to noise ratio in order to measure this. So that is why we use this lock-in amplifier. It provides us with such a high signal to noise ratio that we can, you see this, the noise in this data is very small. It's almost negligent. So
Vishwas, I just have a small query. The first peak is okay, but I can see on your left side of your graph a very clear peak around 1.7. Why it is missing in the derivative?
So see, you might see that okay, this is
this is very pronounced one, so I should expect there is a peak around 1.7. And why it is coming around 1.85, though there is no any
there is nothing. Okay, so this reflectance, there can be many things that are happening, but not everything will give rise to a PR signal.
No. My question is, this feature should appear. Means if I compare to the
you
peak
cannot,
to peak,
you cannot say that this feature should appear.
Because it is derivative. No, you said that there is small curvature change. The derivative should happen. That is what my understanding. Because at least it should show some peak. If may meaning or not, that is another level of question. I am saying that
see, you are seeing over this scale that there is a peak, but when you're taking derivative, it matters. Derivative is within which energy range. Over that energy range, if it doesn't find any any shift, let's say.
So the first thing is the right side is basically a different measurement. It's the photo reflectance measurement.
I know, but what he's saying is
the right side is not the derivative of the left side actually.
It's not the derivative, but derivative features show up in the right side. But not.
It is analog of that derivative.
Yeah,
what he mentioned.
Can I make some comment here?
Yeah.
Yeah. So the thing is, it is derivative spectrum. That's true, but derivative with respect to what? You can take derivative with respect to electric field applied, derivative to laser you are shining, derivative to magnetic field. So probably it may happen that there is a peak in there in reflectance, but with laser intense, when you are shining laser there, the peak is shifting in the both side, and the magnitude or any parameter is not changing. So basically, with laser on, the feature, what is the feature? With laser off, the feature is the same. Then why you will see that any signal in the PR spectrum? The PR spectrum shows that when laser is on, the feature is something. When laser is off, the feature is another thing. The difference between those two is you see as a signal in PR. But if it happens that for that peak around 1.68 or something, with laser on and with laser off, that feature doesn't change any shape or any parameter. So that will not.
So basically, you are saying it is not then a derivative of that left-hand side curve.
Yeah, derivative with respect
it's not
to
the
laser.
derivative of that.
So it should be clear. Wait a minute. So I have a plot y versus x, whatever it is. So you mean to say that it is not a derivative respect to x. Is it correct, Dibya Shankar?
Yeah, exactly. That's some.
Yeah. So
what
that
is
should have been clear.
variable
Okay.
you are using. Yeah.
So that means it can be. So that means you don't know that it is derivative or not. You just say that this is just a change.
Yeah, change. We are measuring the change in the spectrum due to the laser light in presence.
I see. Now it is.
No, but if you see this signal, what you are getting here, you can simulate it as a derivative of this. That is what I was saying. What signals you get here?
Exactly, Vishwas. What I am saying that if you take this curve and numerically derivative, I can also sit with you. I can see that this is definitely give a peak. I am damn sure.
But so we are not saying that is what we will get. So this is not a derivative of this peak.
Now it is clear. That is what he mentioning. It is not actually a derivative. It is just a change. Just a on and off, what Dibya Shankar is mentioning. Now that is clear.
And these features have derivative nature. Like you can simulate it using I'll explain later. So these features are this thing and these two things are coming due to something known as excitons. So this is because of presence of excitons in bulk gallium arsenide. So let me first explain what are excitons. Okay, so if you might know that if you have a direct bandgap semiconductor and you measure its absorption, it will go something like this dotted line here. It will increase as to the power half of photon energy. Now, but in many semiconductors, if you measure this absorption, especially at low temperatures, you see that the absorption spectrum doesn't look like this. Instead, it looks something like this. You find some sharp lines, and then you see such a response in absorption. So what is happening here is these are due to formation of excitons in the sample. And what is an exciton? Let's say you have a valence band and a conduction band, and there are some electrons and holes present. Holes at the top of the valence band and electrons at the bottom of the conduction band. Now, these electrons and hole can recombine, which will give you light, and that's a simple picture. But this electron and hole can also form a bound pair, a bound state. Like in case of a hydrogen atom, the electron and the proton, they are in a bound state. Similarly, The hole here is like a quasi, positive charge particle in in the semiconductor. They can also form a bound state, and because of that, it will and now it has a binding energy. So it will lie, if you see in energy spectrum, it will lie somewhere between the band gap of the material. So that's why before the band gap you see these sharp lines. And now it can also have excited states, like in case of hydrogen atom. So you might see more than one, n equals to 1, n equals to 2, and then they'll combine into the continuum. So and like this is fairly common. Okay, and now the binding energy of this exciton can be given by this formula: mu upon n square me epsilon r square Rydberg, which is ry is the Rydberg constant, which is 13.6 electron volts. Mu is the reduced mass of electron and hole, and epsilon r is the background dielectric constant of the material. So
EN is negative or positive?
This is negative. I haven't put the negative sign, but because it's a bound energy, it's negative. Okay. I'm just calculating
in
the
last figure.
Huh?
In last figure, those bound states are, I think, above Fermi energy. Because the Fermi energy is supposed to be in exactly at the center of the top valence band and the conduction band.
So yeah,
these lines are drawn above, I think, above Fermi energy. So it means they have positive.
Means they have. So the binding energy is. So this, let's say, is the band gap Eg. Binding energy will be so Eg minus this. So this is the binding energy actually. You're taking the energy from the conduction band. How much it's below the sorry, bottom of the conduction band. How much it is below the conduction band is what this here. This thing is the measure of the binding energy. Okay, don't be like this is not an accurate picture, because these bands are drawn in the 1 electron picture, and this exciton is the two particle thing. So you cannot actually visualize this in this picture. But I just wanted to show that these exciton levels lie lower in energy. Okay.
At least they lie just below the conduction band, not above the valence band.
Or no, you cannot when you're talking about excitons, you don't talk about this conduction band, valence band. It's wrong to say they lie what is their energy positions.
No, they cannot form without a gap actually. They will form only if there is a gap.
That is true. They cannot form without a gap. But you cannot assign them.
So then the exciton energy levels, will they be close to the valence band or will they be close to the conduction band?
So that is something that is wrong to say, because when you're talking about valence band, conduction band, you are talking in the one particle picture.
So what I'm saying is, suppose I have a material and I'm measuring say from one side I'm measuring this photo-electron spectroscopy measurement, and from other side I'm measuring this absorption measurement. So from photo-electron spectroscopy I can find the bottom of the valence band. Okay. Now, if you know the bottom of the valence band and you know the top of the valence band and the energy of the top of the valence, that you can find out from the inverse photo-electron spectroscopy or from this photo absorption spectroscopy also. Now I know the position of these two bands. Okay, and here also you can get the energy values of the excitons.
But so what do you get?
Then you know the positions also. The position from the how far will it be from the top of the...
You can only know the position from relative to the band gap of the material. You cannot from the valence band
close to the bottom band, the valence band or the conduction band, isn't it? Is that you're saying?
No, I'm saying you can know the position of the exciton relative to the band gap of the material. That
but
is
not exact position.
It's actually wrong to talk about what is the position.
Okay.
Because it's a different phenomena now. You cannot stay in that the 1 electron picture, 1 particle picture, and say okay, the exciton levels lie here or there. You can only know okay, there's something else that is happening, and it has a energy. It has a binding energy, so that defines its position relative to the band gap.
Okay.
Okay.
Actually, I was expecting close to the valence band, because if it is close to the conduction band, then the energy difference is this energy is little higher than if it was close to the valence band. So suppose the exciton levels were close to the valence band, then probably the energy of the system energy will be less than the current situation, like if they are close to the conduction band. But anyway, we can discuss it later.
That's what I'm saying. It's actually wrong to say it's lying close to the conduction band, valence band. When
we can discuss it later also.
Okay.
I also don't know anything.
Okay. So this is the formula, mu upon n square me. So let me give you a feel of the numbers. For gallium arsenide, the epsilon r is somewhat close to 12.8, and mu is 0.05 me. Let me just show that this electron and hole masses depend on this curvature of this valence band and conduction band. Okay. So you can get an effective mass of what is the effective mass of electron, what is the effective mass of holes. From there, you can get the reduced mass, which comes out to be 0.05 me, and the binding energy that you get for the first, like the ground state of exciton, is 4.2 MeV. So this number is very small. So if you saw, okay, Rydberg was 13.6 EV, but this binding energy is actually quite small. So even like say at room temperature, you wouldn't have seen those exciton like features. It's only at low temperature that you can see them in case of gallium arsenide. Okay. Next, if you want to model what is the change in the dielectric constant of the material because of the presence of excitons, that you can do using something known as the Lorentz oscillator model. The formula is given by this, where A is the oscillator strength. Basically the strength, okay, how intense is the exciton peak, and in some way it's telling you, okay, how much dominant the exciton feature in the sample is. And then epsilon naught is E naught is the energy of the exciton, and gamma is the broadening parameters. So in real world, whatever sample you measure, you will never like theoretically this should be a delta peak. These excitons should be deltas with very small broadening, but in the real world you never find such delta peaks. You actually find some broadening. So you find that there is some broadening related to the feature. That's why you introduce this gamma, which is your broadening parameter. And now this you can this is a complex function. You can plot the real and imaginary parts. So this real part of the dielectric constant will mimic what you will find in the reflectance. So if you were to do a reflectance measurement, this is the kind of response you expect from due to the presence of exciton. And if you were to do an absorption measurement, this is the kind of response you expect because of the presence of an exciton. Okay, just remember this. This is the oscillator strength, and okay, this is gamma. Okay, I'll come to this later. Now let me come to the material that we talk about today, which is MoS2. And MoS2 is a transition metal dichalcogenide. It has the formula Mx2, where M can be tungsten, molybdenum, rhenium. These are all transition metals. And X can be some dichalcogenide, sulfur, selenium, tellurium, etc. Okay, and these the crystal structure of these materials looks something like this, where these blue balls are the metal atoms, and these orange balls are the dichalcogenide atom. And now you see here all the bonds are satisfied within this one layer. So in a single layer of MoS2, since all these bonds are satisfied, and in in between layers, they are only attached using van der Waals forces of attraction. So between layers, there's actually a very weak force of attraction only, and within this layer, they are held very strongly. And so you can actually peel off this one layer, and this remains stable, that it doesn't deteriorate over time. You can form stable monolayers in these systems. That is one thing that is unique about them. And these materials have an indirect band gap in the bulk form. That is, their conduction band and valence band don't align in the the crystal momentum space. But there was a renewed interest in TMDCs in 2010 when this group of KF-MAC, they published that if you form a stable monolayer of MoS2 and they did a photoluminescence measurement and confirmed that it actually transitioned from an indirect bandgap material to a direct bandgap material. It has a very nice direct bandgap, and that too it lies in the optical within the optical range, somewhere around I think 2 electron volts, and it very the monolayer is also very robust. So there was a renewed interest in TMDCs after that, and there have been lots of studies of various TMDCs because of this. Now, because you can fabricate many devices, if you want to do opto-electronics, you can do with these kind of materials. But today's study will focus on the bulk form, not on the monolayer form, because even in the bulk form, it has that is what we find, that it has a quasi-2D nature only. Okay. Now, one thing to note is, if you look at the real picture, like this is a picture of a WS2 sample. These samples are flaky in nature. So if you were to do an optical measurement, this presents a problem because if you just shine a light, there are many planes here, so the reflected light can go in all directions. So your signal goes down. Now, to overcome this problem, we made this setup where we made some improvements over the one that I showed you earlier. So basically, we have put an objective in the path of the light that was coming from the monochromator. And now this monochromator, so this objective increases your spatial resolution, so you can focus the light onto a very small part of your sample. Now, but this presents a problem because now you can no longer see the sample, what part of the sample you are probing. So you can put a white light and a camera to actually image the part of the sample that you are probing, and then you align these two beams together so that all this light is falling onto your sample. So this is an image. So this red light is your probe beam, the beam that is coming from the monochromator. This the white light is imaging the sample, and this green is the laser. Now this is just for the representation purpose, so that you can see all this light correctly. But when we are actually measuring it, this laser spot completely overfills this probe beam. So like the region which is being probed should be completely perturbed by the laser, ideally. That only you get a good you get a good photo-reflectance signal. Okay, so and this is how it looks. This is the cryostat. These are the objectives here, and this is the monochromator from which the probe beam is coming. The laser you cannot see in this thing, and this is a PMT detector. Okay, now let's go into the measurements in case of bulk MoS2. Okay, so this here is the reflectance plot of bulk MoS2. Now, one thing to note is, you see this very big signals. In case of gallium arsenide, they were very small. There was one peak which was very small, but here you see such an intense peaks, which you can again simulate using that Lorentz oscillator model, and you get there are 3 exciton present that you can see even in reflectance. So from here you can say these have high oscillator strengths. That's why you are seeing some intense peaks. And now, why are you seeing these 3 different excitons? First, let's talk about why you're seeing these 2 excitons, A and B. Now, in these materials, there's something called spin orbit coupling happens, whereas this valence and conduction band split into 2, and the spin of each band gets locked. Okay. Now, an exciton forms when a hole from the top of the valence band and the electron from the bottom of the conduction band combine and binds together. Now this can happen only for like the spin of this band, and this band has to be of a certain order, then only that exciton can form. So basically there are some selection rules. And now this spin of an electron that is here can also go down, can come here, but that is known as spin relaxation. But those time period are actually quite high. So these, for the time in which an exciton forms, uh, they remain separated, and that is why you see these two excitons, like such an intense excitons, uh, because the spin involved in the electron and hole is different, and then they survive. Like usually, what you expect is in a semiconductor, if you have electron and hole, they should be at the electron should be at the bottom of the conduction band, and hole should be at the top of the valence band, and you do not see higher excitons. But in this case, you are actually seeing these high states. So that is what is A and B, and because of that, you can actually find what is the spin orbit splitting, and which is roughly 200 MeV. And same thing you can see in the absorption also. You see these three features, and like I told you, you can simulate them, and this is the imaginary part of the Lorentz oscillator, and you see there. And now, what is this A star? This is what we want to find. What is the origin of this A star is. Okay, so for that we go on to photo-reflectance. Okay, so now this is the photo-reflectance spot. So we are now measuring in a smaller range, only from 1.8 to 2.1 electron volts, and we are neglecting the B. Now in R, you see only two features here, but in PR, you now start to see three features, even in that small energy range. And now this, the black one is my measurement, and this is a very complex looking signature. Now, how do you simulate it? Like I told you, this is like PR is it has a derivative nature. So you take those derivatives of Lorentz oscillator model. You assume, okay, the laser is changing the energy a little bit, or is changing the broadening parameter, and you can simulate these features. Now you need at least three such features in order to simulate this data. So that is why I see actually in PR we are seeing three features instead of the two in R. And but here there's a problem. When you have such signatures which are very close by, like they are overlapping with each other, it is actually hard to simulate. So you can see that this fitting here is not that good, because you can play around with the parameters and you can fit. So this is one problem with this method. But now the interesting thing is, in R, this A is very intense, and A star is very small compared to the A exciton, and you don't actually see anything else beyond that. But in PR, these three features are of are almost similar magnitudes. So as if this A star and A dash are actually getting modulate modulated much more intensely than this A feature. So yeah, so that now this is one difference between this the three signals, and we wanted to know what are the origins of this, so that we can say something about the sample, the MoS2 in general. So the next study that we did was a temperature dependent photoreflectance. So these are photoreflectances at different temperatures. One thing you see is they are shifting towards higher energy as I'm going down in temperature. That is because the band gap increases. This is a general phenomena. As you go down in temperature, the band gap increases. Okay, and the signal earlier it was broadened because at high temperature you expect the broadening is increased. So the exciton itself is broadened. So this is also a problem. But as you're going down in temperature, your signal tends to increase. You tend to see these three, nice features. But now, if you go down in temperature further, the signal again, stops or reduces in strength. If you had like in the reflected, if in the reflectance measurement this doesn't happen, that keeps on becoming sharper and sharper. But the photoreflectance is what is going down, and this is what can be the cause. It could be that the charge carriers which are involved in their motion is what is modulating this and giving rise to the photoreflectance. They are freezing as you are going down in temperature, so they are not as mobile as they are at let's say in the 100 Kelvin or 150 Kelvin region, because of which the signal is going down. And the next thing to notice, the three features don't have similar behavior with temperature. This middle one, the A star, it, actually, it's becoming more intense here, while the A and A dash are going down. And at the lowest temperature, you still see some presence of A star, but the A and A dash have completely disappeared. So one clue that we get is this A star is has some different origin from A and A dash. And now what can it be? In this TMDCs, because I told you like they in one layer you have strong covalent bonding, and the dielectric environment in this layer is quite different from if you were to measure it along the C-axis, because here the layers are close, not that strongly bound. You have weak van der Waals forces. So what happens is this electron and hole they tend to reside within one layer. Like if you want to see the wave function of this entity, it tends to reside within one layer. And then there can be a possibility where the electron and hole are residing on the adjacent layers. Okay, and like in this picture, it's showing electron and hole here, but hole can also be, for this electron, hole can also be on this layer. So this is something known as interlayer excitons, and the other one was interlayer. Now, interlayer excitons have been studied in these systems, but usually how they study it is they put two different TMDCs layers together, and now they are different environment, and they show that this interlayer excitons exist. But recently there have been studies that even in the same material, like this is just bulk MoS2, there also you can have the existence of these kind of signatures. And so that is what we wanted to find out, whether this A star is a signature of an interlayer excitons. So that is why our collaborator Thorsten Tillman did some theoretical studies, and we tried to compare our experimental data with those studies. So first thing is you can get the electronic band structure of whatever your material is, in our case this MoS2, using something known as density functional theory. And then there are some higher order approximations that you can do, and you can get a good EBS of the material. But usually it's the energy positions are not that accurate, but like they can, depending on how much is your this thing, how big of the region you are of the mesh you are using to get this thing, and they can change. But once you get this electronic band structure, you can also calculate the absorption spectrum of your material using something known as the Bethe-Salpeter equation, which is the quantum field theory equation for hydrogen atom. In that you just replace the electron and proton to electron and hole of the material that you have, change the background dielectric permittivity and all, and you can get a absorption spectrum. Here also this this kind of this calculated spectrum depends heavily on how big of a size of the the sample mesh that you are using to calculate it, and it can deviate, but still this is done with a reasonably sized mesh, and you see these three features come up. This is a exciton, intense, and then it shows that there is something which he has labeled as I, can also come in this system, and then there is an equals to 2 and something, and this is the band gap. And one more thing that you can do is you can plot the wave function spread of these systems. So how you do that is you assume that the hole is residing in this layer, in the center of this layer, and then you plot how the electron wave function looks like for in the sample. And for n equals to 1, we see that the electron wave function mostly resides in that layer only. So it has this, for a 3D semiconductor, you would expect that there's a uniform, wave function in, like, you would have assumed a circular kind of thing, but here you see that the wave function is mostly confined to a single layer. So that's why we say this is a quasi-2D system. It's not exactly 3D, and it's also not 2D because it's a quasi-2D system. And now for this next feature, you find that the wave function is mostly in the adjacent layer. So that's why we concluded that the A star that we were seeing there is actually an interlayer exciton. And the next signal that was coming in the photo-reflectance spectroscopy is actually an n equals to 2, which has a spread like this. Okay, so this was our final conclusion, that the two features that we see in photo-reflectance spectroscopy are an interlayer exciton, and the A dash is the first excited state of the A exciton. Now, because now we have the ground state and the first excited state, we can calculate the binding energy of the exciton, and which comes out to be 77 MeV. But this has been calculated using a 2D model because that seems to be more accurate in finding these binding energies. Yeah. Okay. So this was my study. If you want more information, you can read this. My paper last year it got published. You can get much more information. I've skipped many details because I didn't want to overburden you. So.
Yeah, I have a question. I have a couple of questions.
Okay.
Yeah, so I missed, I think, your first two slides or first three slides. So I am confused, like when you are doing this measurement, you are using a lamp with a monochromator, so it is already selecting a wavelength, right? Yeah. And then again you are using the laser. So why these two type of lights you are using, means wavelengths you are using, or are they same?
These are two different things. This is like the light from the monochromator is probing our sample. It's what is measuring the and first of all it's continuous. Okay, so it's not changing with time, and it's a low intensity light which is just measuring like we are collecting the reflected part. Now the laser is actually there to perturb our sample. It's I showed here that there's a built-in electric field. The laser, it's an intense source of light. It's actually changing that built-in electric field a little, and that change is being measured with that probe beam. So that is why I'm using this tool. Does that answer your question?
Okay, so from this monochromator, so what is the wavelength of this light, or it is a simple low intensity light?
You can change the wavelength. That is the actually the use of monochromator. So let's say here I'm plotting from 1.4 to 2.0 photon energy. So yeah, I can change the wavelength. This is using one monochromator only. I can do a scan. So that is the.
Yeah, and one more question. So does this measurement gives you the band gap, or just only we get excitons from these measurements?
like there have been systems where even for some samples you can get the band gap. So where the band gap exists, you get a structure in PR. That has, but it depends from sample to sample.
Because here, if you see in this gallium arsenide, so the peak that is coming is around the band gap, the high intensity peak, right?
But that is not because of the band gap. So yeah.
The peak that is coming around 1.5, that is the band gap, right?
At low temperature, yeah, the band gap is what? I don't remember, 1.6 or 1.7 something. No. So yeah, so in gallium arsenide, the exciton binding energy is very small. It is only 4.2 MeV. Okay, so band gap will be very close to this point, but we know that this feature is not coming from the band gap. This is actually coming from the exciton.
Okay, both the peaks they are okay. Both the peaks are from the excitons. You're saying.
This is a heavy hole exciton and light hole exciton of the gallium arsenide.
Okay. Okay. So you showed the PR measurements of bulk MoS2, right?
Yeah.
And that was around like 1.8 and 1.9, 2.1 like that. So actually my confusion was, are they coming around the band gaps only?
So now again, like I calculated this for MoS2, the binding energy is 77 MeV. So if for A exciton you assume the energy is somewhere here, you can with simulation you can tell what is the actual energy, and if you shift it by 77 MeV, you will get somewhere here is where your band gap exists.
Okay, and this was bulk MoS2 means this is indirect, right?
This is indirect, but even in indirect, okay, maybe I forgot to mention this. Even in indirect, there is somewhere where the direct band gap exists, right? So that is where we are probing it. So let's say here in the electronic band structure. So this is indirect because the top of the valence band is at the gamma point and the bottom of the conduction band is at the K point. So this is the indirect gap. But at the K point is where the fundamental direct band gap lies, which is the lowest direct band gap lies at the K point. So this is where we are actually probing when we're doing this, all these R and photoreflectance. This is the point where we actually measure, because you will still get some response because this is also a local minima. There will be some electron holes there, and this is why you're getting this kind of response. So when I say this is a indirect band gap material, that is, if you let's say shine a laser of high intensity, you won't get any emission out of it, or a very small emission, because once the charge carriers get excited, they tend to accumulate here at these points. So and they cannot recombine radiatively because they are separated in the momentum space, and photons have a very small momentum. So that's why it won't give any emission. But like when we are measuring the reflectance or absorption, we are actually measuring the density of states of the. So here there is still some density of states which can be optically probed. That's why you're measuring the optical.
Okay, so that means the MoS2 that you use, it has a direct, means it was the direct semiconductor.
No, it is an indirect band gap material. It has an indirect band gap, but we are measuring near the direct band gap. So
actually, I got confused because I know that bulk MoS2 is an indirect band gap semiconductor.
So yeah, that's what I'm saying. I'm not saying that it's not an indirect band gap, but when you are if something is if a material is an indirect band gap material, it doesn't means that it cannot you cannot probe the the part where it is direct. It indirect band gap means the lowest energy separation of the valence band and conduction band is at a point which is not lying on top of each other at the K space.
Yeah, but then For example, like monolayer, if you take a monolayer of MoS2, so that is direct, right? You will get direct, which means it is a direct semiconductor, but bulk MoS2 is indirect. Then how you are saying that we can probe it at the direction sign?
Can I comment something?
Yeah.
So I think what Vishwas is trying to say, this is not band gap, we say it as optical band gap. So how you can probe this material with optics? So with light you cannot do a absorption or any measurement from gamma to K point, right? So the K of light is very small, so you virtually do a line transition on the K axis. So with with light, you can probe only from like in a fixed K from one band to another. So the material is indirect band gap, that's true. If you see the energy diagram, it is indirect band gap material. But with the optics, we are measuring the optical band gap, and optical band gap is a K point, and which is actually not the minimum energy. So you cannot say that is the band gap. That is optical band gap, what we are measuring.
Okay. Yeah. Because the excitonic peaks that you are getting now, so that is around like 1.1 or 2. And
that is not actually the actual band gap of the material.
That is not the fundamental band gap of the material.
Yes.
With optics, what you probe is that. You can only probe that part. You cannot probe the fundamental band gap using optics.
Okay. Yeah. Thank you. Thanks.
Hi Vishwas, nice talk. But I have still one question. I always curious about that question. Why not excitons can form in a intra band? Like why not excitons needed always a band gap?
No, it's not a point of you won't be able to observe them, no.
Let's say
your question is why do you not see them in metals? Is that your question?
No, my question is let's say in the semiconductor still, let's say I am at the 0 Kelvin temperature, okay? All are in the valence band electron. Now I increase the temperature, some electrons go into that conduction band. So now creating a hole in the valence band, and the electrons are in the conduction band. So valence band, in the valence band still there is electron.
But those are
why not there is creating, huh?
Those are not free. They are not free to move around.
Yeah, but that is my I'm questioning why you need the mobility.
Okay, let me give you an example of hydrogen atom. Let's say you have a hydrogen atom. If you separate the electron and hole, you have two free electron and hole, right? Now let's say you just have a hole and there is a hydrogen atom here present, electron and hole. So can it take the electron from that proton and combine to form another a hydrogen atom of itself? That is not energy. It will require some energy, right, to take it from there and come here.
No, why you are saying this mobility is important? I am asking you the free. No, suppose I have a positive charge. If it is around, it's a negative. Always it can form bond. Why it is a mobility is important? I am asking you the fundamental point of view.
I'm not saying mobility. They have to be free, na. You can form bound state of something of two free particles. You cannot form bound state of a particle which is free and something which is already bound, because at the end you then end up with the same thing, na. You just move it from one place to other.
I see.
You can form a bound state of two free particles. So. You might remember.
Now I got it. Now the second thing is, another question is which one is the most energetically favorable in your this intra band or the and the inter band? Which one in the case of a MoS2? Yeah.
Layer, intra layer or inter layer.
Yeah.
So
which one is more favorable?
The energy of intra layer is more.
Okay.
So that is it's at a lower in the energy, if you plot it.
This is always true.
For these like TMDCs, because there is a high anisotropy along these two directions. That's why for these in this case, intra layer is much more,
Nice. Okay.
efficient. Yeah. For let's say gallium arsenide, in gallium arsenide case, you don't even talk about interlayer, because you have a uniform 3D lattice, so where electron and hole are moving around.
Nice. And another thing I maybe missed in this case, when you decrease the temperature, why this signal is going down and down? Can you just repeat
So
once again?
what I was saying is, in R, if you go to lower temperature, this will become even sharper.
Mm-hmm.
Okay? Because your broadening is reducing.
Mm-hmm.
There's a component of thermal broadening. There's also a component of inhomogeneous broadening. How good your sample is, on that it will also depend how sharp your this thing is. Okay. So now at a low temperature, this thing is getting sharper.
Mm-hmm.
But in PR, so if something is sharper, if there's a sharp exciton, you would expect the derivative to be even more, right?
Mm-hmm.
But that is not what happens when you go down from 100 Kelvin to 10 Kelvin. It keeps on decreasing.
Mm-hmm.
So what can the reason be? Your exciton species themselves are becoming sharper, but the modulated signal is actually going down. So basically, the modulation mechanism is its strength is reducing as you're going down in temperature. Okay, so that modulation that I showed, the
Causes that why?
the cause of that is what I was saying. These charge carriers might be freezing. That I don't know for sure, but that is a speculation that
I see.
these charge carriers, their mobility is is going down. I tried to do a Hall measurement, but it wasn't successful. But
With temperature.
With temperature.
Okay.
But I think I saw a paper somewhere which mentions this, that as you go down in temperature, the mobility decreases in these materials. Yeah. So this is one signature of that. Yeah, because the mobility is decreasing, so the modulation mechanism is going down.
Vishwas, there is another way to explain it. So as you decrease the temperature, Herbig distribution will be more sharp. So then you have less number of conduction. And
Less number?
in the conduction band, there is no recombination.
There will be more recombination, no?
No. If there is no electron in the conduction band, there is no hole
So
in the
he's
valence
saying
band.
that as the temperature is decreasing, your number of excitons is become lesser and lesser. Is it true, Vishwa?
No. That's what I was saying. Here in reflected spectrum, this is very sharp. So as you're going down in temperature, this is.
Then the question is, Vishwas, then why is then the first the way you have explained the excitation formation, why that number is not gone down? Because as I reducing the temperature, there is a lesser and lesser number of the conduction electron.
No. So those are thermally excited electron and hole, right? But when you shine light, you are creating electrons and holes, no?
So this is by this modulation itself it is creating.
No.
This means when you excited, then it is created.
No, you don't even need modulation. Just the probe light. When it reaches this, the photon energy reaches this level, the electron and hole can form an bound state. Okay, you don't need thermally excited electron and hole. Even at 0 Kelvin, if you did, you will find this. There are no thermally excited electron and hole.
So there is no point of that. What is saying this Fermi-Dirac function? It is not playing here any role.
Yeah.
Okay. So it is just you have by probing you are just creating this electron and the hole excitation and exciton are forming.
There is a density of state exists in the sample itself. So okay, whose signature we are seeing here.
What is the laser energy?
A laser is 532. 532 is what, 2.33, I guess.
Somewhere around 2-3 eV.
Yeah, that's why you see up till here. Yeah. But that's what I'm saying. Like, to see excitons, you do not need a laser. You just shine any probe light also.
And how much sorry, another thing I just want to know, how much integrated role play by here spin if I see this diagram, this was. So this when this pairing is happening, this does it more favorable than upspin, downspin, or it is like a both upspin, upspin?
No, okay. So this was for representation purpose only. This
Yeah, let's physically or whatever the measurement, whatever the
what I
papers
wanted
are
to
there.
show was ki, the valence band and conduction band of certain spins only form an exciton, and of the other spin form this exciton like this. Like, these two will be involved in formation of one kind of exciton, and these two will be involved in the formation of the other kind of exciton. So there is an energy shift. That is what you are seeing here, A and B.
Yeah, I am asking that.
Now, if these spins were to relax quite fast, then you wouldn't expect to see this A and B. You should have seen only A. Because B is
I'm not asking this. I am asking that this formation of the bound state is which one is more favorable? Is the both are the spin are aligned in the same direction or in the opposite direction?
That is, you'll have to go through the theory key, which one is favorable.
No. If somebody has doing this experiment, what is this result?
Exchange integral term. That depends on the exchange integral term, but that's difficult to calculate here actually because these things are intra-band exchange terms. So unless you have detailed information about these bands, you cannot calculate.
That's why I'm saying that experimentally has anybody has proved or not, because calculation is very difficult because itself is a complex system.
Yeah, what people show is that there's a difference, but they don't go into the detail key what is the actual spins.
Yeah, so I just wanted to say, I don't know whether it's a correct statement to make here, but you see, this is Vishwas has not gone to that level, but the structure is a hexagonal structure. If you see for MoS2 and all these TMDCs, it's a planar hexagonal structure. And if you go to the Brillouin zone, then there is also an hexagonal structure, and there in each alternating side of hexagon, they are actually different. Like here, Vishwas has shown that upspin.
No. We are not talking about this spin Gali coupling. We are not talking about that.
That will confuse people.
So, are you seeing these two peaks every time when you measure A and B?
Yeah. They will occur every time.
Okay.
So this is the.
You were saying the band gap will change with temperature. Why?
So the band gap usually increases as because the what you say these lattice vibrations are going down as you're going down in temperature. So because of that, there is some broadening associated here with the conduction and valence band, which tends to reduce. So they become more sharper as you go down in temperature. So because they are becoming sharper, so the band gap is also increasing. This is a general formula, like for all semiconductors, you'll see this. There's actually an equation. I forgot the name, but you can actually model how much is the shift with temperature, and you can calculate some parameters also. This is like you can correlate the phonons in your system with the shift of the band gap.
No, but band gap won't change. No? That band gap is basically the peak position.
Okay. If you say in that terms, yeah, means what we are measuring as a band gap that changes. Yeah, but like what you theoretically calculate is calculated at the 0 degree temperature, right? Whenever you are at a certain T, you will have some, these lattice vibration effects will come into the picture, and yeah, you will see broadening. So you in a way, yeah, you can say that the band gap is only changing. Band gap changes with temperature.
But generally, Vishwas, how I just have a simple this extension of his question is just to know that how much is value is generally changed. Let's say at 0 temperature, my band gap is V0. So generally, what percentage is generally changed from your experience?
Okay.
Just to
Here,
tell me if you
let's
can.
say at this is at room temperature. Let me what should I focus? Okay, this peak. Let me focus, and it's changing like this. After that, it's small, so we want. So let's say from 300 Kelvin, you went to 100 Kelvin, and you see a shift of roughly what 300 or 400 or even more, 500 MeVs. No, not 500, 50 MeV. Sorry, 50 MeV.
50 MeV will change after a certain time. One more thing, it is what is your error in your measurements, this delta, what is the resolution? Because the last graph I am saying you are multiplying 20 factors so to see this feature. So what is the general resolution limit that you call it the noise level? Feature is always appear just to I know that what is the general noise level this delta or measurement?
So up to -4 of the let this should be minus here. So this is in 10⁻⁻3. So the R, let's say, was 1 volt. So you can measure up to 100 microvolts. Up to that,
100 microvolts means 0.1 millivolt. Okay.
that much change you can measure, and you can improve upon that using more averaging and all. But
No,
usually,
that's okay. That's I want to know because always like since you have multiplied a factor by 20 to see that feature. That's why I want
so
to know
that's why
that
you
what is
see
the noise
this
level.
noise also is
So that's the noise level. What is to call
it's
it
a
feature?
kind of noise level. Yeah. But here, if you see, this hasn't been multiplied, and the noise is virtually there is no noise compared to what is the signal. So one is the thermal broadening because of temperature, and the other thing is how good your sample is. There is some inhomogeneous broadening related to if you had a perfect sample which is free of all defects, there's no doping, nothing, then the broadening would be related to the lifetime of your this thing of your exciton. You remember that delta E delta T? That would be your ideal. That would be the ideal thing. It's not like very poor. This is like in general you will see this kind of broadening always. So like this feature that you see here is because this is actually a very good sample. It's very hard to get such a clean signal here. This is a years of research on gallium arsenide has produced such a good gallium arsenide that you can get such a good signal. Yeah. So that's so no. It could be that there is this is due to some like there is something happening, but the thing is you can use more than 3 peaks to even simulate this, but you need to know what is the cause of that. So we didn't know why. So in that case, we won't know why such a small peak is coming, and what kind of exciton can exist there. Like we need to have a understanding of what excitons can exist in these systems and what can be the cause. So we don't understand what is the cause of this. Yeah. These can be there, but we are no way of you know like confirming that is what is happening. So that's why we left it there. Okay. Uh, okay. Yeah. You cannot, like, if you had a cake like this, you cannot cut it along this direction. Okay. You have to cut it in this direction only, but you want two equal halves. Oh, only one cut. One cut from uh, two halves. Only one cut with a knife. Let's say. Okay. Okay. You change your screen.
What was the question? Probably I joined little.
Okay. So the thing is, let's say you have a cake. Okay. You have a cake of rectangular shape. Now you cut a rectangular piece from somewhere within the cake. Now that rectangular piece that you cut can be in any orientation and can be of any size. Okay.
Yeah.
You have cut that out. Now you have left whatever is left. You want to have two halves of that cake that is left with a single cut of a knife. And you cannot cut in this direction. You just have to cut in this direction. How do you cut it? You want to have two equal halves. Okay, I'll stop presenting. Mhm. Okay. Uh-huh. Oh, wow. But how do you cut this with a knife? A single cut with a knife, no? So this cannot be done with a single cut of the knife. Okay. Let me make it even easier. Single from one end to the other end of the cake. Single cut of knife with one end. But this is too complex. It's very hard to. Hmm. Uh, I want some practical solution, not some theoretical solution. I want to eat the cake. No, you don't know the area of the green. You don't know the orientation. Nothing. Okay. So let's say every rectangle has a center point. If you join the two diagonals, it has a center point, right? Now, if you cut along with the center point, like in your cut, if you cut along any two points of the rectangle, you will always have a two equal halves. This you can try. Any cut that includes that center point will always cut the rectangle into equal halves. Hmm. Now you make any cut along using with the center point in that cut. You will also. So this will always give you 2 equal halves of the rectangle. No. So I'll come to that. So that is a general fact. Now you have the center point of the bigger rectangle. You have the center point of the smaller rectangle. You make a cut joining these 2 points, and you will end up with the 2 equal halves of the rectangle. Okay. Okay. Thank you.